Thank you. So thanks to organizers, in particular to Abhishek, to invite me here. And I must in advance apologize. There's also of that, but that is the talk is not really connected with large deviations. I never worked on large deviations, so I could not, in 2 months, prepare a talk on this. But hopefully, it is connected to some topics that you might be interested in. Okay, so this is a work that I did by myself, but I benefited from discussion with colleagues, in particular my colleague in Dauphine, François Simoneau's, Michele Salvi, which is doing a postdoc in Dauphine, and then Florian Vollering, with whom I have discussed several times on related issues. Okay. So what is it about? Well, I want to speak about a random walk, or if you prefer, a passive particle that is driven by a fluctuating surface. So the equation is this one. So xt is the position of this blue circle, the particle. And this is the surface. So the surface is described by 2 terms. So there is a fluctuating term, which I called f for fluctuations. And then there is some drift term v, right? So the equation is of that form. So what it does, sort of, is if here it is pushed to the right, into this local minimum, and then the surface will evolve in time, and it will be pushed in another place, and so on, right? And there is a parameter lambda, which is an inverse. It has the dimension of an inverse time, so it's a rate, and this determines how quickly the walker reacts to this environment. Okay, and the drift term. I'm actually, to be frank, what I'm interested in is the behavior of this random walker of passive particle, and I'm interested in the case where there will be no drift, but I saw that it would be interesting to approach the no drift case by a small drift case, and so think that this drift is just a small number. Okay, so let me give some comment on how does it fluctuate, the surface? Well, the fluctuation this is usually called the Edwards-Wilkinson class of fluctuation. So well, first it's a fluctuation. So if you put it in equilibrium, then there is no drift. It's sort of no bias. It's balanced, and it obeys a diffusion equation of that form. So if you forget the xi, then you have just the diffusion equation with a diffusion constant d, and then I add some noise. And what is this xi? Well, it's white noise in time, and I put some correlation length L in space. So what is this L? It is this L that stands here. So if you would put white noise both in space and time, then it would be a rough surface, and then even the meaning of this equation would be unclear, and that I don't want, because this is not the kind of problem that I'm interested in here. Okay. I will speak more about this field, but sort of this already gives the main sort of definition, right? So yes, I would say this talk, no mathematics, right? Only some reasonings or heuristics and numerics. Okay, and okay, you see now that there are 2 rates. So there is lambda, which is this rate that was here in front. So how the walker reacts to environment, and there is the diffusion constant d, and it's, if you wish, useless to keep two constants with same dimension, and you could actually say that all the model is entirely controlled by lambda over d and by the external velocity field v, which are both dimensionless. Okay, so just to make it clear what it means to be, how should you think of fxt? Well, it's something that is diffusive. Diffusive means on a length L in space, the height is of order square root of L, and the relaxation time is square over d. So that's quite standard. So this is the of a Brownian motion, except that it is locally, it's smoother than the low. Okay. So give a formal definition, and this is useful both because for the numerics I use this. I mean there I need to use a specific definition, obviously, and then also to think, I think it's helpful, this definition. So if you go to Fourier space, then you can write this velocity field as a superposition over modes, and those modes are just like those independent sines or cosines, right? And independently, and so there are two terms in the definition, right? This object here is the cutoff over on the high modes. So that means that this is smooth on the length scale, which is L. And to make those slides a bit simpler, I will take L equal 1 in the torque. So that means that I fix a unit so that L equal to 1. And then here are all the modes, and you see they are related like that. So K and K prime are independent, and then there is relaxation in time. So you see that the low mode, for example, this yellow one, so this, if K is small, then wavelength is 1 over K, and relaxation time is very large, so 1 over K squared, basically. And this high mode, which is this blue one, relaxes much faster than the yellow one, okay? So this turns out that this was relatively convenient to simulate numerically this field. And it's also useful to think for some theory, because it really expresses all the scales that appear in the problem, and it decomposes all the scales that are there. Okay. And then, okay, this is not, you should not necessarily remember this slide, but I would like to mention that for those of which are it is very much related on some lattice. So this was, for example, studied by Avena and Thoman in 2012. So I just want to put a small dictionary. Obviously, if you are not used to it, then this dictionary will not be useful for you. But so let's say you have simple exclusion process, which will be the blue particles, and then the Walker. So there is only one Walker, but I wanted to represent the Walker in two different positions. So the Walker is the red one. And so this minus dxf plus v, which is the velocity field that I'm talking about, become simple exclusion process with a density which would be 1/2 in the neutral case plus some small v. The diffusion constant of f becomes the diffusion constant of the simple exclusion process. And the coupling strength lambda that was in front, so let me just remind you, right? So I'm used to the notations, perhaps you are not, right? So this lambda that was here, which determines the reaction of the Walker to the field. That would, for example, becomes the jump rate of this Walker, right? So if the Walker is on top of a particle of the simple exclusion, it jumps to the right. If it's on top of an empty side, it jumps to the left. And so this might be considered a discrete version of the problem that I was introducing before. So if, for those of you who prefer things that are in discrete space, then you can also think of this model. Yeah, no. It is the case that I'm interested in is V very small, right? So that does not. And one could also, I mean, you see here that all the randomness come from the external field. One could also add some Brownian motion, for example, on the wall itself, and I tend to expect that this would not too drastically change the picture. Okay. So perhaps, why should we be interested? Well, one obvious reason, although in my opinion perhaps not the best, is that it's very natural to have an environment that becomes diffusive. If you are in one dimension, if there is a single conserved quantity, then this conserved quantity evolves diffusively. Hence, it is very common, because energy is always conserved, to have a diffusive environment. In my opinion, a better reason is that this problem is very puzzling. So the fact is that in dimension 1, the time correlation decay very slowly, right? So you have, it is polynomial with exponent 1/2. And this means that there will necessarily be memory effects. I mean, it seems very excluded that you could represent this Walker as a just independent sum of independent increments. That does not seem to be the case. So there will be huge memory effects, but it's a priori at least very unclear in what direction this will go. What will be this effect, sort of? So upshot is hard to predict. And in fact, I found rather little. I mean, the problem that I want to address, I found very few references in the. I mean, there are a lot of references that go around this problem, but that really deal with it, I found very few only. So there was a paper by Gopalakrishnan in 2004 that I will speak about in some detail. And then there was some numerics by Avena and Thoman that I already mentioned before. And there are plenty of other papers, but that really deal with the point that I want to deal with. I found only those two. Okay, and now let me say you the questions that I will ask. So there are four. So the first question is it so that this walker will reach a non-equilibrium stationary state? By this I mean, in some cases, we know that random walker in random environment can see there is the equilibrium measure of the environment, and if you go along with the walker, you can observe a new invariant measure, that is the invariant measure as seen from the walker, and this measure usually differs from the a priori equilibrium measure of the environment. And this is what I would call the non-equilibrium stationary state, because here it's probably, there is little chance that this will be an equilibrium measure. So yes.
But then there is a question if the function f, or rather its gradient in space, does it equilibrium? Does it equilibrium?
Okay. So right. So perhaps that I did not say you are right. I forgot to say something. So the field itself. So this one, or rather its derivative, right? So this one here, I take it to be in equilibrium. So the external field is in equilibrium, but that does obviously if you now go along with the walker, that does not mean that you still see this equilibrium state typically, right? But you are right to point out that I should have specified that this field is in equilibrium, because if you take it out of equilibrium, it will add an extra layer of complexity, obviously. Okay. So that would be my first question, whether for V positive or zero, whether you reach this non-equilibrium state. Then the next question is, okay, now consider the velocity of the walker given the external drift. So big V is the velocity of the walker, so the asymptotic velocity of the walker, and little v is the a priori drift. How does big V behave as a function of small v when small v is sent to zero? Next question is, if there is no external drift, how does fluctuate this walker, right? So there are two exponents. One would be alpha, one would be beta. So given this conference, I could add a next question: what are the large deviations? But I did not study it yet. And also important is, do those answers depend on the parameter lambda over d? So the ratio between those two rates. Okay. And those questions are related, right? Because it is known that you can understand a lot about a physical system by studying response to a small external field, and the best known example I think is linear response or Einstein relation, where there is a relation between fluxes out of equilibrium or close to equilibrium and diffusion in equilibrium, right? So that was a first set of examples where there was an interesting relation. And for systems that are out of equilibrium, there are some generalization of those linear response to system out of. I'm not really a specialist of it, but as far as I understood, all those generalizations are based on the fact that, at least on the fact that, and much more things, that the walker or the system has reached some non-equilibrium stationary state. So the three questions that are here, I think, are strongly correlated among them. Okay. And now let me come to start giving not answers but possible scenario for this. And I come to a distinction that was introduced in this paper of Gopalakrishnan that I was talking to you, and he distinguished two different regimes. So first regimes would be when this coupling strength of the walker to the environment is very strong, or if you wish, if the diffusion constant of the field is very small. Then what happens is that this walker will stick to local minima of this field, and it will evolve slowly, and it will always follow those minima like that, right? And that would be like quasi-static in the sense that it's almost like if it were static, and it is sort of trapped by the environment. And then there is another regime, which is called homogenized regime. And in this case, when lambda is very small, or if the diffusive field evolves very fast compared to the Walker, what one sees is that, okay, the Walker is there, and first he sees some velocity on the right, which is the dark gray curve. Then the field evolves, becomes the light gray one, and then pushes the guy in the other direction. And you see the Walker stays there, and he sees the field evolving there, and does not react instantaneously to the evolution of the field. And for those two cases, in this paper, there were two different predictions for the behavior of the Walker. At least for this question, for the fluctuation. This was not analyzed, but this was analyzed. Okay, so. Okay, let me try to give heuristic for both of the cases. Okay, first case. So let's first go in this case where you are trapped by environment, and let's try to be interested in this velocity of the Walker as a response of the external velocity. Well, what you can do is, okay, you have the external velocity, which is this constant v, and if you average the fluctuation field in a box of size 1 over v square, then the amplitude of this average is of the same order of this field v. So this red curve is also of amplitude v, and this one is as well. And since this is diffusive, the time to destroy this small mountain is of order 1 over v over 4, right? Because this is the square of 1 over v square. And what the interpretation is the following, that this will also be the time to just pass across this region. Why? Because if v pushes you to the right, then it's also logical to think that this red curve here, then, or let's say this one will push you in, for example, in the opposite direction if the signs are opposite. Hence they compete, and to pass it you would need to wait this time. And so if you believe this, what you find is that the velocity, well, this is space over time. Space is 1 over v squared, and time is 1 over v4. And you find that the velocity of the Walker should scale quadratically with the velocity, with the external velocity. So this extremely heuristic reasoning would give this answer. Okay. What about fluctuations? Well, fluctuations say the following, right? So the blue curve is the field f at time 0, and the orange curve is the field f at some time of order L squared over d, and you look in a spatial scale which is L. Well, you see initially the Walker was trapped somewhere here in some local minimum here, and then this fluctuates, and this pushes this Walker all over the places, and it tends to go to some other local minima of the field here, right? And typically something that is quite low compared to the top of the mountains, which is here. So, and you can imagine that it has brought the Walker from here to there, which is hence a distance of order L. And so if you look the square, then you get L squared, you get a distance L squared, right? And then you find from this, again, extremely heuristic reasoning that the variance should scale, that would be normal diffusion with a diffusion constant that would be the one of the external field. Okay. I don't mean that this is correct, but that's it. I mean, this is sort of a guess, if you wish. And now let's look at the other regime. So the regime which is the regime where the Walker is almost free. So let me just show you again. So now this regime, right? So the field evolves fast, and the Walker evolves slowly as compared to the field. Well, in this case, what was proposed is that we could do some self-consistent approximation. So what it is? So you see initially, I mean, equation of motion, if you integrate, you get this equation. So this is just the integral version of the differential equation that was written before. And the approximation is to replace, it is very hard to solve, right, this problem. And if you replace here xs, another thing ys, that may become easier. And what is ys as compared to xs? It's if you wish another Walker, which evolves completely independently of the environment, but has the same law as x. So it's a Walker that should have the same law as x, but is not at all influenced by the environment. And obviously, you try to determine y and x so that they have the same law. I mean, you have to solve now this problem, and it is already much easier than solving the previous problem. And if the Walker indeed is not trapped, then there is a chance that this approximation gives a plausible answer to the questions that we are asking. Okay, so let's try to solve let me not try to justify the green arrow, the approximation. Let me try to solve the second part, right? Well, for the velocity, it's quite simple. That's direct. So if you just want to work the first moment, well, what do? You take you average on the left and you average on the right, and since y and f are independent, average of this part vanishes, and you are left only with v times lambda t, and that's the upshot that is there. So that means that from the point of view of this approximation, they say, no, not quadratically, but rather linearly with v. Then you can solve for second moment at v equals 0, and that's already a more complicated task. So what you do, you write this equation, and so that's obvious, right? And then you have to cheat a bit more. So there is a next approximation which I think is not harmful. So you see, now you can express this, but in fact, for knowing the second moment of x square, you should know the full distribution of ys. So it's not closed, there is not a closed equation for second moments. However, if you do Gaussian approximation, then there will be. And so do proceed, right? So do a Gaussian approximation, then second moment of this is related to second moment of that, and you find an equation between, I mean, they must coincide because we have imposed that y and x have the same second moment. And you find that x squared t behaves like lambda t to the 4/3, right? So the prediction is that it is a super diffusive random Walker, yes?
Well, the assumption on the force F is needed in order to find the 4/3 exponent.
Well, the field F is what I told, right? So this is this one, right? So there are those correlations. It's Gaussian field with this. So yes, so that did not change, right? So the field F is as before. Okay, so you find super diffusive prediction, and Florian Vollering is preparing a paper where he justifies part of what I write, and part of what I write, what does it mean? So justify mathematically, I mean, it does not mean that it justifies this approximation. So it does not justify that this equation can be replaced by this equation. That's purely heuristic. It justifies how to solve the problem of finding x and y being independent and having the same distribution. I think there is also a Martingale term in this case, but I mean, you should ask him if you have questions on that. Anyway, just to say that those kind of conclusions in this approximation can be justified at a higher level of rigor than what I'm doing. Okay. And we should be a bit suspicious about this self-consistent approximation. And why? Well, in some sense, I think to be valid, well, I mean, you see the Walker Y, so this one, right? He just visits the environment and he's not influenced by the environment. That means that for him, he sees a bit the equilibrium measure of the environment. There is no correlation between him and the environment. So for this approximation to be valid, I would expect that there should be a non-equilibrium stationary state for the Walker, and this would in some sense resemble a bit the neutral equilibrium measure of the field. If that is not the case, then one will probably be in trouble with this approximation. If you want to think of this from a dynamical point of view, what it means is that at all scales you should have fluctuations that are always strong enough so that you overcome all the trapping effects that the field produces. I will a bit come back on this. And an extra warning is that a thing that mathematicians know very well is this Sinai random walk in static environment. So just put the diffusion D to be 0, right? So then you have just a frozen environment. And you could apply this same self-consistent approximation to this case. Why not? After all, so there is also a parameter lambda. So it could be that the Sinai random walker is almost like a free random walker, except that there is some small inference of the field. And you could say, perhaps we may apply again self-consistent approximation. And what turns out is that self-consistent approximation in the static environment gives the same super diffusive prediction. So it gives also that x squared t would be lambda t to the 4/3, and that we know is not correct. No, I just meant the following, that if you apply it, you will get a wrong answer. And you are saying, yes, you should not apply it because you are trapped. I agree with you entirely, except that you don't know in the problem that I am not interested in, I don't know in advance whether or not I am trapped, right? So just to say that there is whether you are a priori trapped or not, right? So you see those conditions like lambda d much smaller than 1 would say, well, you don't seem trapped, but that does not mean that you are not eventually trapped, right? So this is the meaning. Okay. Yes. No. I mean, yeah, okay, yes, I understand. So no, I mean something else. So I mean the invariant measure of the environment seen by the walker. So that means, for some cases, for example, if there is fast mixing of the environment or things like that, you can follow the walker, and there is an invariant state of the environment as observed by the walker, which is a bit different from the equilibrium state of the environment. Okay. So before doing more theory kind of things, let me just say what numerics, some my own numerics. I mean, there have been some contradicting numerics, so I think that my numerics are just the best, but it's obviously an arrogant position, but okay. So I will proceed in 3 steps. So the first thing is that I first want to measure the time to stationarity at v bigger than 0. That is important because, but first for practical reason, if you want to measure the velocity as a function of v, then you better would know how long you have to follow the walker. And also for theoretical reason, because if that is a long time, then it may hint at some interesting things. For example, that as v goes to 0, you perhaps will not reach any stationary state. So that seems to me to be first question. Next is to ask about this velocity as a function of external parameter in the limit of v go to 0, and then fluctuation. And from what I could observe from those numerics and later from some theoretical-like arguments, I detected that the walker eventually was always trapped. So that means that this self-consistent approximation seems never to be accurate. There may be important finite size effects, and there may be some corrections that is logarithmic-like. I did not test that they are really logarithmic, but there seems to be also corrections with respect to the first scenario that I was mentioning. So none of them was precisely correct. I think this one, so the self-consistent approximation looked clearly wrong, and the prediction from the trap regime seems basically correct, but not perfectly, to be frank. Okay. So let's start with this issue of how fast do you reach stationarity. So let's take v bigger than 0. And now what to do? Well, let's split the fluctuation field into 2 parts. So I now use this decomposition in Fourier modes because I find it slightly more convenient than doing special average, but it's eventually the same thing. So you do a first slide where you have only the very low modes, which are of amplitude k at most v square, and then the ones that are higher, which are k bigger than v square. And k smaller than v square, why do I decompose it that way? Because this first part of the field has an amplitude which is of order v, which is just of the same order as the external field v, which is here. And the one on the right, now that you have this cutoff on the low modes, this is something that will get refreshed This is now fast mixing, although with a very slowly in the terms of this coefficient, but in the mathematical sense, fast mixing. And so this will be something that will be entirely refreshed after time 1 over d v squared. And so the idea is that since this is of the same order, let's assume that this constant c is very small, so this is even much smaller than the external field v which is there. Since it is much smaller, let's just ignore this term. Right? It is an extremely, it's like replacing v by 2v plus epsilon or something like that. Okay, that should not matter. And if you do so, the big advantage is that now, if you say, okay, bye-bye this first term, then this is fast mixing, and hence you have a guess for the time to stationarity, and this time would be just the time which is the refreshing time of this field, so 1 over v to the 4. Okay. So this is already a conclusion because we have to test it, right? But let's say if that is correct, then what it means that the time to stationarity diverges as I approach v equals 0. In particular, one is tend to think that at v equals 0, you may never reach non-equilibrium stationary state because the time would become actually infinite. So this already makes this self-consistent approximation to collapse sort of and answer part of the questions. Okay. So let's look at it from numerical point of view. So let's test the prediction on one observable. Since it turns out that it works rather well, I just took this observable. So let big V of little v and small t be approximation at time t of the velocity, right? So this is a quantity that obviously is supposed to converge to this. And let me define a rescale time. Well, so let's fix t star will be the time at which it is supposed, this limit is supposed to have been reached. So it scales like 1 over v to the 4, and I took a constant k that was actually pretty large. For some reason that could explain, but that means there may be some other effects here. And then instead of having this v as a function of v and t, let's call it this curly v as a function of the rescale time. And let's compare those objects. Okay. And if you do so let's say first lambda equal 1, which was, so for all the numerics, d is 1, right? So lambda equal 1 means actually lambda over d equal 1. So if I compare, there you have various curves that you almost don't see because they are almost coinciding, right? And each curve is for different small v, and then you plot this. So this is supposed to converge to the drift v of the Walker, and since we don't know a priori how that will scale, I just divide by this, and what you see is that those curves seems to collapse pretty well, which seem to indicate that indeed this scaling in 1 over v4 was a correct scaling, right? So you see that for the green curve, for example, which is here, the time is, this 1,4 is 1 over 2 to the minus 5 to the 4, so 1 over, 2 to the 20 actually, proportional 2 to the 20. While for the blue curve, it is a much smaller time for the 1 basically, right? So there has been a huge rescaling here. Okay, so that is for lambda equal 1. Let's see whether something changed when lambda goes down, right? If I take now something which is less, a priori less trapped, so more towards the self-consistent case, well, okay, lambda equal 1/2, then you see that this blue curve changes a bit, but okay, but the picture is nearly sort of similar. If you take lambda equal 1 over 8, well, you see that some curves start to be a bit off, but that's not yet a problem, right? So the blue and the orange are the rather large value of v, and what we are interested in is the limit of small v to be 0. So for small v, collapse is still quite good. So interpret that, okay, if lambda is smaller, pay attention, there may be important finite size effects. Okay, same is true for, I didn't go further than this, but if you go to lambda to 1 over 16, you see some discrepancies, right? But what the good news was that for the last two curves, so the smallest value of v, there was still very good agreement. So, okay, so that means from those numerics and from the heuristics that I sort of reasonably trust this prediction that the time to stationarity scales like 1 over V4. Okay, okay. Now that we have this information, we can move to exponent alpha. Exponent alpha is how big V of V scales as V, right? So if you take a logarithmic plot in Bosquet's, then okay, here is the slope 2 line, right? So that means that if alpha is equal to 2, those curves should approach this red line as V is going to 0. So here V goes to 2 to the minus 5. And for this light blue one, which is lambda equal 1, so the case that was most favorable to be trapped, that seems to go not too bad. Well, for the other one, in particular for the very light blue here, so you may say, well, that's less clear. It's indeed less clear. The good thing still is that at no moment we see a crossing of those curves. I mean, if at some point this light blue should need to go to slope 1, as is predicted by the self-consistent approximation, then they should cross the other curves, and that we don't observe, right? And the situation is perhaps still a bit better if you, instead of plotting the curves themselves, let's now plot the slopes of those curves. And so that those are the slopes, I mean the discrete approximation of the slopes. And you see well that for lambda equal 1, you go pretty close to the value 2 for the exponent alpha. And indeed for the lambda much smaller, well, you are increasing, then it's a matter of belief whether or not you are going to 2, but at the very least, anyway, you are drifting away from the value 1, which was the one predicted by self-consistent approximation. So seems to be that there is at least some trapping, even perhaps. Okay. Fine. So now we can look at fluctuations. So let me try the scaling the diffusive scaling, right? So let's try to plot it. So now the external V is 0, and let's plot that diffusive scaling. And for lambda equal 1, well, you see that this it looks all more or less okay, but not exactly, right? So there is the impression that there is some logarithmic correction. So you go to 2 to the 16 to 2 to the 26, right? So it's quite a wide range of increase, and this increases very mildly from 9 to 11 or so, but still I cannot hide that it's slightly increasing. So obviously don't know whether this is a true effect or a finite size effect, what will happen if you would look at much longer times, but at least there is the possibility that there is a logarithmic correction, and for some other reasonings, I think that it is actually plausible that they are there, but I think I will have no time to explain it today. If you look at even much smaller value of lambda, up to 1 over 32, then you may, from this plot, you may really doubt whether that was the right scaling. I mean, you see some curve which is moving upwards like that, and it is not obvious that this was correct. So let me plot the same data in an order scaling. Which one? Well, the one that is predicted by the self-consistent approximation. So self-consistent approximation says that x squared t behaves like lambda t to the power of 4 over 3. Well, and if you do so, that was, you see this remarkable feature that, okay, first this increases to a value which is, okay, 1.6, I don't know why. And then in all the cases, it starts, after some transient time, it starts to go down, right? So I interpret that observing this scaling is like a finite size effect, because you see that it may be huge, right? If you look at lambda equal 1 over 16, at time 2 to the 22, it looked like a perfect way to scale the data, but then it starts decreasing. So one may imagine that if you would take lambda even smaller, that you would still have plots of that kind. Now, a question that you may ask is, why is it that you don't observe, for example, for this very light blue curve, just a plateau like this, and then, whoops, drops like that? Well, there seems to be a lot of finite size possible scaling. So for example, so okay, I will be finished, right? So for example, here, for this part, you can think that the walker is essentially does not move and sees the environment moving, and then the approximation that you do is you replace the velocity field at x by the velocity field at 0, and you find another scaling that would be able to justify this. So there are a lot of possible scalings that are here. Okay, I have no time to go beyond. There are some theoretical, well, okay, I will completely drop, right? Anyway, okay, so I just wanted to say as conclusion that most important to me was that it seems that you don't reach stationary state, that there is no linear response. So in that sense, the system is very far from equilibrium. So and that I found some way to detect trapping, both by looking at the velocity and both by looking at fluctuations. And point 4, I did not have time to speak about it. Okay, so thanks a lot for your attention.
More questions? Frank?
So the self-consistency approximation is apparently clearly wrong, and so this has to do with the fact that there's really a strong interaction between the walker and the environment, in the sense that you cannot brush this away. Would you be able to do something a bit better by saying, I'm not letting YT to be a completely independent copy, but some sort of smoothing of your XT? So you smooth it a little bit, and maybe depending on what the smoothing is, you could see some kind of crossover in your results, or would that be technically still as difficult as just doing the whole problem originally?
Well, I did not. I mean, if you meant to do something mathematical with that, then frankly I don't know for the moment. So that I did not really. Well, obviously it's something that we thought about, right? For example, with François, we thought first, I mean, you have this field, and initially there are a lot of fluctuations, and let's assume that those fluctuations go down as time goes on, and then you reach something that is smoother and smoother in time, and then you see that this trapping is there, and we could make that more or less precise, but the connection with the initial problem was too loose, and then we did not investigate. So that we thought a bit about those ideas, but not in a very detailed way.
So your equations are still linear, right? So isn't
No.
I mean, like linear in noise, right? So
Well, the equation for the field is.
yeah, but this other one is linear in the field, and the field is linear in noise. So isn't that a Gaussian process? And I mean, in principle, can't you write down a solution?
But I mean, the basic equation looks not linear, right? Because
I mean, these are linear differential equations, no?
Well, perhaps we don't mean the same thing, but if I
I mean, like if you just
this one, right? So this is a nonlinear. I mean, this coupled nonlinearly.
no, it's linear. It's still in F, right? I mean, so if you write down a Fourier Laplace transform, I mean, it will be some messy equation, but I mean, in principle, you can still
Linear in F, you mean?
yeah,
Yes.
Linear in F, and then F equation is linear in the noise.
Yes, that's right. Yes.
So if you do a Fourier Laplace transform, I mean, in principle, you have a closed form equation. I don't know whether you can extract something from that or not, but
Transform in the time variable, you mean? Both.
I don't know. Okay, maybe you can.
It's not clear to me. Okay, bon. I think I don't understand clearly what you want to do. Yes, you want to do a Laplace transform, but
So what I mean is that F is linear in noise, right?
Yeah, that's right. That's right.
And then since F is linear in noise, isn't it this X also linear in noise? Some combination of noise?
So you think that X depends linearly on this noise psi, which is here? I don't see this. You could be right, but that I have not realized.
Other questions?
So right now from the numerics, it's not clear what the exponent is. Is that right? I mean,
Say again, please.
from the simulations, it's not clear what exactly the exponent is. Is that, I mean?
No, no. So
I mean, is the,
for this one is sort of
the fluctuations?
for fluctuations. No, it's not. I mean, this looks like a logarithmic correction, but the other one is not.
That looks like power law, right? I mean, it's,
Right. The only thing was that this one is not correct, but that does not mean that we know exactly what it is. Yes. I mean, if you look only at simulations, I agree with you. So the numerics do not say at the end what would be the right. If you look only at from numerical point of view, the right. Yes, I agree.
Other questions? Okay, I have just one. Usually when you look at trap situations in a random environment, you are looking, okay, trap, but there exists some motion. However, you look at the environment seen from the particle.
Yes.
So here you are sitting on the particle. Can you derive? Here, of course, the environment is moving with time, but it's just another source of randomness in your equation. But you still can try to see how the environment, the grad x of f evolves seen from x of t. Did you think about that?
I thought about it, but it confused me too much, and I stopped because I had in mind, okay, if it's sort of trapped, then for each mode you are more or less more in the valleys than on the top, but you cannot be too much because otherwise, I mean, if you are in the valley of this one, then you are not in the valley of this high one. So where are you at the end of the day? And okay, I could not see a clear picture. I did not succeed with this approach, let's say, to say anything.
Okay, so thank you again.
Thanks.